Hi, this is MD Shabana Sultana, working as an associate professor in the Chebrul Engineering College, Chebrul. Today, I want to discuss about the non-elemental semiconducting material. What is non-elemental semiconducting material? That means semiconducting materials are classified into two types. They are elemental semiconductors and non-elemental semiconductors. What are semiconductors? Before going into the classification, that is elemental and non-elemental semiconductor material, first let me know you about what are semiconductors and what are the property of semiconductors. Semiconductors means the material which behaves as an insulator. Insulator means the substance which does not conduct the electricity are known as insulators. And material which behaves as an insulator at absolute zero and conduct the electricity at normal temperature. That means the same material, it behaves as an insulator at the absolute zero and conductor at normal temperature is known as semiconductors. That means it is behaving either as an insulator as well as the conductor based on the temperature. At absolute zero, it behaves as an insulator. At normal temperature, that is at the room temperature, it behaves as a conductor. That type of materials or that type of solid substance is known as semiconductors. And coming to the property of the semiconductivity, it is explained based on the band theory, which I'll explain later. And this semiconducting material, it is classified into two types. They are elemental semiconductors and non-elemental semiconductors. Coming to the first one, that is the elemental semiconductors. These are the conductors that are elements, and the examples are silicon, germanium, gallium, etc. Non-elemental semiconductors, it is again of two types. They are stoichiometric semiconductors and non-stoichiometric semiconductors, which I'll explain later. And these semiconductors, it is of two types. They are intrinsic semiconductor and extrinsic semiconductor. These semiconductors, this classification, it is mainly based to explain the property of the semiconductor, which depends on the band theory. I told that I'll explain later this one. Coming to the first one, that is the intrinsic semiconductor. If the energy gap or the Fermi energy gap is small between, see here, this is the valence band, which is having the low energy, and the electron present in this valence band is known as the valence electron. If we supply the energy externally in the form of temperature, then whatever the electron which are present in the valence band absorb this energy and get excited and jumps from the valence band to the conduction band. And the electron, soon after reaching into the conduction band, This electron is responsible for conductivity. Conductivity of semiconductors. So, the gap which is present, the energy gap which is present between the valence band and the conduction band is known as Fermi energy gap. Fermi energy gap. Coming to the intrinsic semiconductor, if the Fermi energy gap is small between the Fermi energy gap is small between the valence band and the conduction band, so that the electron from the valence band is excited. The electron from the valence band is excited to the conduction band is known as intrinsic semiconductor. Both the hole and the holes left in the valence band and the excited electrons in the conduction band. Both the holes left in the valence band and the excited electron into the conduction band contributes towards conductivity. As the temperature raises, that means whatever we are supplying the external energy from whatever the energy which is supplied externally is known as external energy. As the temperature in the form of temperature, as the temperature rises, the number of electrons promoted to the conduction band increases, contributing to the increase in the conductivity of semiconductors. Coming to the second type of semiconductors, which are known as extrinsic semiconductors. See here, I told in the intrinsic semiconductor, the Fermi energy gap between the valence band and the conduction band is small. Then it is known as intrinsic semiconductor. Whereas coming to the extrinsic semiconductor, if the Fermi energy gap between the valence band and the conduction band is moderate, that type of semiconductor is known as extrinsic semiconductor. See the figure. So this is the valence band and this is a conduction band and this is a Fermi gap. The gap is fulfilled. The gap is fulfilled between the valence band and the conduction band with impurities is known as doping. Doping means adding the impurity to fulfill the energy gap, Fermi energy gap between the valence band and the conduction band is known as doping. And this doping is of two types. They are N type of semiconductors and P type of semiconductors, or N type of doping or P type of doping. Coming to the first one, that is the N type of semiconductors. The best example for the elements which are used for N type of semiconductors are pentavalent impurities, like the fifth group elements, like phosphorus, arsenic. If it is doped to silicon or germanium, then this type of semiconductors is known as N type of semiconductors. See, coming to the mechanism, how the N type of semiconductors will be formed, I already told that the elements like pentavalent elements, those are considered as impurity. These pentavalent elements have 5 electrons in the outermost or valence shell. Out of this, that means 5 in the 5 electrons, in that out of 4 electrons is bonded to silicon or germanium. See here. is a pentavalent element which is having 5 electrons. 1, 2, 3, 4, 5. Out of these 5 electrons, 4 electrons, 1, 2, 3, 4 electrons are bonded to the adjacent silicon. What about this electron? This electron is known as surplus electron. This surplus electron, it is wandering in the semiconductors. By wandering from one place to another place, it conducts the electrons and conductivity increases. So this is a doping of impurity. This is a valence band and this is a conducting band. This is a donor band. That means whatever the surplus electron is wandering, it jumps from the valence band to the conduction band. And the dopant with more electron form a narrow band. Next, coming to the p-type of semiconductors, by introducing the trivalent impurity. In the n-type semiconductor, I told you that is a pentavalent impurity. Here, trivalent impurities are used in this type of semiconductors, like aluminium, boron, gallium, indium, and thallium. 2, silicon or germanium. What will happen is, the replacement of this silicon or germanium atom by the impurity produces an incomplete bond with the structure. See here. In the structure, if the trivalent element, if it is placed, trivalent element is having the trivalency. That means it is capable of forming only 3 bonds with the adjacent atoms. This trivalent, it forms an incomplete bond in the structure, producing a positive pole. This positive pole, see here, it forms a hole. This hole are localized around trivalent impurity atom at low temperature or absolute zero. At normal temperature, the valence electron on the adjacent silicon or germanium atom may gain sufficient energy to move into the hole, thus creating a new hole on the silicon or germanium. By a series of holes, the positive hole can migrate across the crystal. Thus, the current is carried out by the migration of positive centers. So this is the figure. Next, coming to the non-elemental semiconductor. This non-elemental semiconductors is classified again of 2 types, which are known as stoichiometric semiconductors and non-stoichiometric semiconductors. Along these 2 semiconductors, there are another 2 types of semiconductors are also there. They are control valence semiconductors and the fourth one is chalcogen semiconductors, which we will study now. Coming to the first one, that is the stoichiometric semiconductors. The crystal structure and the band structure similar to that of the silicon and germanium, are developed by the combination of two groups, that is group 3 and group 5 elements and group 2 and group 6 elements are named as stoichiometric semiconductor. That means they are following only a particular gas, their combination is satisfied only a particular group of elements. The combination of the elements like group 3 and 5 are group 2 and 6 and certain other compounds which have the valencies is in the non-stoichiometric composition. This stoichiometric semiconductors, the example for this, if the gallium and arsenic here, examples, the gallium and arsenic, if you take this type of semiconductor, the gallium is having the electronic configuration of 4s2 4p1 level and arsenic is having 4s2 4p3 level. That means they two gets overlap and gives rise to a hybrid band containing 4n electrons per n atom of gallium and arsenic with Fermi gap of about 1.34 electron volts. If we take this gallium phosphorus semiconductor, it is having the energy gap of about 2.24, and gallium and strontium, they combine together to form a semiconductor with a Fermi energy gap of about 0.67 electron volts. And coming to the another type of semiconductor, which is known as indium and arsenic combinated semiconductor, which is formed with the energy gap of about 0.36 electron volts. And coming to the second type of combination, that is the group 2 and group 6 combination. In this, here, the cadmium and sulfur, they both are combined together to form a semiconductor with the energy gap of about, Fermi energy gap of about 2.42 electron volts. And coming to the cadmium and selenium, it forms a semiconductor with the energy gap of about 1.74 electron volts. And lead and sulfur, PBS, lead sulfide. Therefore, it is also one type of semiconductor which is formed with the energy gap, Fermi energy gap of about 0.37 electron volts. So this is about the stoichiometric semiconductors. Coming to the characteristic of the semiconductor. Stoichiometric semiconductor have wide energy gap, which leads to the broad exhaustion zone with high conductivity. Hence, they can be used at wider range of temperature. It is possible to alter the energy gap of these semiconductors by substituting one of the elements in its composition by an element of lower atomic number belonging to the same group. For example, if you take the gallium and phosphorus semiconductor, if phosphorus is replaced by the arsenic, the energy gap is reduced from 2.24 to 1.35 electron volts. That means it is possible to alter the energy gap of these semiconductor by substituting one of the element in its composition by an element of lower atomic number belonging to the same group. That we have to be remembered. The alteration of the energy gap by substituting should be from the same group, not from the different group. And they can be doped to N-type or P-type of semiconductors. Coming to the non-stoichiometric semiconductors, this type of semiconductor possess vacancies in their structure and non-stoichiometric compositions. They also behaves like N-type or P-type of semiconductors. That means the metal attached with the chalcogen elements like oxygen to form two or more different semiconductor material is known as non-stoichiometric semiconductors. In this type of semiconductor, it does not obey the Arrhenius theory of electrolytic dissociation. What is Arrhenius theory? According to the Arrhenius theory, the number of anions is equal to number of cations. That means if we take the example, that is NaCl, by passing the electricity, it undergo electrolysis and dissociates into Na plus and Cl minus ions. That means whatever the Na plus ions will be formed, that is equal to Cl minus ions. That is Arrhenius theory of electrolytic dissociation. But this non-stoichiometric semiconductors, it does not allow the Arrhenius theory means the total number of anions is not equal to total number of cations. So the Arrhenius theory of electrolytic dissociation, it is not following which one non-stoichiometric semiconductors is not following. That means the total number of anions is not equal to total number of cations. Example this one. Fe plus O, that is FeO, Fe2O3. And for example, if you take the zinc oxide, it is formed by exposing the zinc oxide to reduced atmosphere where some Zn plus 2 are reduced to Zn plus ions, which is richer by one electron and can donate an electron to promote the conduction band. There creates a donor level band between the valence band and the conduction band. I'll explain these controlled valency semiconductors as well as the chalcogen photosemiconductors and the preparation for the semiconductors in the next lecture. Thank you.